Welcome to Learning with Philemon. In the previous video, we learned the theory behind nuclear magnetic resonance and analyzed low-resolution spectra. In this video, we will look at the extra level of detail that high-resolution NMR spectra provide. In the previous video, I mentioned that the chemical shift is a relative scale. This means that the resonance frequencies of the hydrogen nuclei are compared to the resonance frequencies of hydrogens in a reference or standard compound. The most common reference compound used is tetramethylsilane, or TMS. As can be seen in the structural formula, TMS is a symmetrical molecule. This means that all 12 hydrogen nuclei are in the same chemical environment. As a result, we see only one strong signal in the NMR spectrum of this molecule. Because silicon is less electronegative than carbon, the hydrogen nuclei are very shielded. This means that they require a low frequency to achieve resonance. This makes TMS a good standard, as almost all other hydrogen nuclei in other molecules will require a higher resonance frequency. To calculate the chemical shift, delta, we use the following equation. As the frequency required for TMS is usually lower than the frequency for the hydrogen nuclei in our sample, this gives us a positive value for the chemical shift. For example, in the 1H NMR spectrum of 1-chloropropane, all the peaks have a positive chemical shift. This is because the hydrogen nuclei require a higher frequency to achieve resonance than in TMS. The signal for the standard is often removed from the spectrum. I have added it here so you can visualize that it would appear at 0 ppm. Now let's take a look at features of high-resolution NMR. As I explained in the previous video, the strength of the magnetic field experienced by hydrogen nuclei depends on the presence of electronegative atoms nearby in the molecule. However, it is also affected by the hydrogen atoms on neighboring carbon atoms. This phenomenon is called spin-spin coupling. In this molecule, we have two chemical environments, denoted as A and B. The magnetic moment of hydrogen nucleus B can be aligned or against the external magnetic field. This actually affects the magnetic field felt by hydrogen A. If hydrogen B is aligned with the external magnetic field, then HA experiences a greater effective magnetic field. This increases the gap between hydrogen A two possible orientations. It is de-shielded and requires a higher frequency to achieve resonance. If hydrogen B is aligned against the external magnetic field, then HA experiences a smaller effective magnetic field. This decreases the gap between hydrogen A's two possible orientations. It is shielded and requires a lower resonance frequency. So instead of seeing one peak for hydrogen A nuclei, the peak splits into two sub-peaks. This peak is called a doublet. Note that the difference in frequencies is very small. Now let's take a look at the signal for hydrogen B. This is slightly more complicated as hydrogen B is affected by the alignment of both hydrogen A nuclei. There are four possible combinations of orientation. If both hydrogen nuclei align with the magnetic field, we get the de-shielded effect. If both hydrogen A nuclei align against the magnetic field, we get the shielding effect. However, it is also possible for one hydrogen to align with and the other two align against the magnetic field. The shielding and de-shielding effects cancel each other out. The chemical shift is unchanged. This sub-peak is taller because there are two ways to get this cancelling effect. The signal for hydrogen A is called a triplet. The splitting pattern that you will observe for a molecule can easily be predicted using the n+1 rule. N stands for the number of neighboring hydrogen atoms on the neighboring carbon atoms. If there are no neighboring hydrogen atoms, the signal will appear as a single peak. If there is one neighbor, we will see a doublet. This was the case for HA in our previous example. The HA nuclei have one neighboring hydrogen, HB. If there are two neighbors, we will see a triplet. This was the case for HB, that has two neighboring hydrogens, two HA nuclei. The ratios on the table show us the relative height of each subpeak. If you are interested in mathematics, this pattern in peak height comes from Pascal's triangle. At IB and A level, you usually do not encounter more than 3 neighboring hydrogen atoms, a quartet. Now let's take a look at an example. Here we see the high-resolution 1H NMR spectrum of ethyl methanoate. There are 3 chemical environments, so 3 peaks in the spectrum. However, we see that some peaks have split into sub-peaks. Let's explain why this is the case. The hydrogens in environment A are the furthest from the electronegative oxygen atom. Therefore, they are the most shielded and should appear at a lower chemical shift. If we check the carbon atom next to these hydrogen nuclei, we see that there are 2 hydrogen atoms, the 2 HB atoms. Using the n+1 rule, this signal should split into 3 sub-peaks. This is in fact the case, as the signal is a triplet, 1, 2, 3. Note that this splitting into sub-peaks is not seen in low-resolution NMR spectra. The hydrogens in environment B are closer to the electronegative oxygen atom. They are de-shielded and appear at a higher chemical shift. These hydrogens have 3 neighboring hydrogen atoms, the 3 HA atoms. Using the n+1 rule, this signal should split into 4 sub-peaks. The signal for the B hydrogens is a quartet, 1, 2, 3, 4. The signal for the hydrogen atoms of the alkyl group of an ester usually appear between 2 and 2.5 ppm. The neighboring carbon atom is not bonded to any hydrogen atoms. Note that whenever checking for neighboring hydrogen atoms, we should never look beyond 1 neighboring carbon atom. The signal for hydrogen C is a singlet. For more on how to use high-resolution 1H NMR to determine the structure of unknown compounds, check the videos on my Patreon page. There you can also find worksheets to practice these skills. If you want to support my channel, check the donation link in the description. If you haven't already, please subscribe to my channel to get notifications for new videos. Stay curious.